Okay, this is our next video on kinematics. I believe video 4. So in this one, we're just going to take a look at projectile motion. Now in projectile motion, this is the path a thrown object will take. The key is to see motion as two parts. We've got a vertical part, which obeys the formulas for constant acceleration, and a horizontal part, which obeys the formulas for constant velocity. So here we have a picture of a cannon firing a cannonball. This top path represents what would happen if there was no gravity. The cannonball would follow a nice straight line. It would never slow down. It would never speed up, so it would have a constant velocity. If I were to drop the cannonball, it would begin to accelerate. In fact, I want to redraw this and make this look a little nicer. So first off, notice that I'm keeping these in line with that one. So you guys see how the spacing changes. So that shows that the object is accelerating. So for the x-axis, and for all these, we're going to use our main model for motion. So for the horizontal axis, we have that. Now, the acceleration on the x-axis equals 0. So what we're left with is that right there. On the y-axis, we have that model. And on the y-axis, the acceleration equals g, which equals, we can basically say negative 10 meters per second squared, or in your math classes, they'll use 32. So basically, we have that model right there. One thing that's interesting about projectile motion, the time it takes for a projectile to land is the same as if you would simply drop it. And I have a demonstration piece I'll show you in class, and it's very, very interesting. But this is something that's counterintuitive, but 100% true. Okay, so let's take a look at another projectile. This one's being launched from the ground at a certain angle. So first off, velocity is a vector. So I'm going to come up here. So if I have an initial velocity of something being fired at an angle, I can take this and I can resolve it into its x and y components. Now notice what I've done here is I have created a right triangle. So I can use some right triangle trigonometry to find this. So remember your SOHCAHTOA. Sine is opposite over hypotenuse. So sine, this v naught y, would equal v naught times the sine of our angle. Cosine is adjacent over hypotenuse, so this v naught x would equal v naught times cosine of theta. And if you go back and look at your summer assignment, I have notes on trigonometry in your summer assignment, so you can go back through there and review that if you need to. So then, looking at this, our range really is the same thing as x. So for the x, or the horizontal component, we have that. And then for the y component, we have that formula. And it's really it comes down to two equations, two unknowns. You should be given just enough information where you have two unknowns, and you can use these two formulas to solve for those two unknowns. Generally, time is an unknown. It's kind of hard to know how long this projectile has been in the air. We'll do some practice problems and some worksheets in class to get better acquainted with the math behind this. But to be perfectly honest, as long as you know these two equations, and really they are the same exact equation, it's just that the acceleration on the x-axis is 0. If you know those two equations, and if you know the trigonometry, you're set. Projectile motion does not have to be difficult at all. A lot of students seem to struggle with it, but I think we'll be okay. Down here, this is just another illustration of this projectile motion. One area where this is going to become very useful is in golf. So expect a lot of golf problems, maybe some basketball problems as well. All right, that's going to conclude video 4 for kinematics.